Okay, let's look at the section 2.9. This section talks about the fundamental properties of logical equivalence. All right, so let's look at them. All right, first one is called the commutative laws. All right, so if you look at P or Q, which is logically equivalent to Q or P. So the order in which you take the disjunction doesn't make any difference. And the conjunction is the same way. P and Q is logically equivalent to Q and P, right? And the second one is called the associative laws, right? So you have three things, you're taking the disjunction of three things, right? So this one, we take the disjunction of Q and R first, then take the disjunction with P, right? But the order in which you take the disjunction doesn't make any difference, so you can actually take the disjunction between P and Q first, then take the disjunction with R, which is going to be exactly the same, logically equivalent. The same way, if you look at the conjunctions, junctions is the same way. You can take the conjunction between P and Q first, then take the conjunction with R. Right? These are equivalent. All right. The third one is called distributive laws. You can actually distribute P or to sort of each statement like this. All right. So you have P or, then conjunction with Q and R would be, you can do a P or Q, and then you do a P or R separately, right? Then after that you take the conjunction, so take the and between those two results, right? And the same way with P and then parenthesis Q or R, we can just distribute this P and to each statement. So we're going to do P and Q and P and R. Then we take the or between those two results. Right? This is called the distributive law. Right? The last one is called De Morgan's law. Right? If you want to negate the P or Q, you can kind of distribute the the not, so it's a not P and also not Q. All right, but you have to be careful when you do that. You're going to have to change or into and. All right, and the same way with not P and Q, so we can do not P and also not Q, but we have to change and into or. Right? Those are the De Morgan's laws. All right. So the use of this fundamental property is this. Here's a good example. All right. Let's say that you want to prove that the not P implies Q is logically equivalent to P and not Q. All right. Let's say we already know that the P implies Q from the previous section is logically equivalent to not P or Q, right? So let's use that. So this is, we verified it by truth table. Truth table. So we believe that they are logically equivalent. All right. So without using truth table, and using this fact and all these, some of these laws to establish this logical equivalence. All right, so let's start with this. All right, so here's left-hand side is not P implies Q. All right, So this is kind of hard to deal with. We don't know exactly how not applies to an implication, but we know that the implication can be written as, right? I'm gonna not part alone for now, right? But the P implies Q is logically equivalent to not P or Q. So we have not P or Q from the previously proven result. All right, then we can use the De Morgan's law right here. So if you take the not of disjunction, right? So you have disjunction here. So we can just take the not of each one. So it's going to be a not P, right? Then you have a not Q as well, right? Then we're going to turn this or into and, right? Then if you have a double not is same as not taking a negation. So double negation is simply P, right? And not Q, right? So you can see that negation of P implies Q is equivalent to P and not Q. So we could establish this logical equivalence, right? So this is an example of the use of fundamental properties, right? That's it. I hope that this was clear.